Welcome to the AP Physics video lecture. This is on Unit 3, Circular Motion and Gravitation. This video is going to be covering centripetal force in the vertical direction. Here's the scenario. In the Dragon Ball Z anime, Goku stays on a small planet and trains. He trains by running around the planet like a circular track. The question: derive an equation for Goku's centripetal force to stay on the circular track using V for velocity, M for mass, R for radius, and the normal force, and any other physical constants. Assume the downward position as positive. The assess part, we are looking for centripetal force, so summation of Fr is equal to our question mark. This direction is on a circular path, and we notice that the summation of Fr has to be equal to mass times centripetal acceleration because this object is not in equilibrium. Let's do the diagram. We assume this to be a circle for the circular track. There's Goku, which is on top of the circle. There's a force gravity pulling him down and a force normal that is opposite to it. Please note that the force of gravity's length here is longer than the force normal to show that it is stronger than the force normal. The force normal is, if the force normal was longer, then Goku would actually fly off the planet. Let's do the summation of the forces. Summation of Fr is equal to minus Fn, because that is upwards, plus Fg, which is downwards. Let's solve. Make the substitution, so it's mv squared over r for centripetal acceleration. Force normal is left the same, and force gravity is just mg. Good. That is the deviation for the centripetal force. What is the source of the centripetal acceleration in this problem? In other words, what is keeping Goku in this circular path? Well, if we look at the equation, we saw that there are two things. The force gravity contributes to increasing it. That's why it's a positive mg. While the force normal is negative force normal. That negative decreases the centripetal force of the system. Here we have the same question as before, the same scenario, but a different question. What is the maximum velocity that Goku can run around this circle and not fall off? So the assess part is now velocity equals to question mark. Everything else here remains the same. I'm just continuing my steps from the last problem. We are looking for this velocity. Please look at the picture. That's the velocity that we're looking for. So we're solving for that v in our equation. Please note that Fn is going to be 0 in this case. The reason why it's 0 is because the maximum speed the object can have without leaving the track. In other words, it means field weightlessness. That is the reason why Fn equals to 0. Fn goes to 0, so it reduces to that. The masses cancel, leaving you with v squared over r equals to g. Solving for v, so you multiply r to the other side, then square root. So the velocity equals to the square root of radius times gravity. Please note that the maximum speed the object can travel in the circular track only depends on the radius and gravity. Mass is not part of it. Next, this is a roller coaster. A cart on a roller coaster track enters a circular loop. You're going to derive an equation for the centripetal force to stay on this circular track using only v for velocity, m for mass, r for the radius, the normal force, and any other physical constant. In this situation, we're going to be looking at the top of the inside of the loop, like where the roller coaster is right now. Please assume the downward is positive. Let's do the assess part. We're looking for the centripetal force. It's in a circular path, and it is not in equilibrium. The diagram, we assume that to be a circle because it's a circular loop, and we're looking for the top of the inside of the loop. Force gravity is downwards towards the center of the circle. force normal is also pointing down. The reason why it's pointing down is because notice it is perpendicular to the surface. That's why it's pointing down. Let's do the sum of the forces. So here it would be summation of Fr is equal to Fg plus N, which is the normal force. Let's solve by plugging in the values. We make the substitution, so it's mass times centripetal acceleration equals to mg plus the force normal. Substitute v squared over r for the centripetal acceleration. That would be our equation for the centripetal force at the top of the inside of the loop. Please notice that both of the forces are pointing towards the center of the circle. So what is the source of their centripetal acceleration in this problem? In other words, what is keeping the object in the circular path? In this case, there are two sources. It's both the force normal, which is increasing it, and the force gravity is also increasing it because they're both adding to the summation. Next, in this same scenario, you're going to be asked, what is the maximum velocity that the car can have here without flying off the circular loop? So we're looking for the velocity. We have the same situation here, and we're looking for that velocity here that we have to see. Notice here, Fn will be 0 because, again, the maximum speed that the object can have without leaving the track. In other words, field weightlessness is when Fn equals to 0. So Fn goes to 0, leaving you with just mv squared over r is equal to mass times gravity. Mass will cancel out, multiply r to the other side, take the square root, you get the same answer as before. Velocity equals to the square root r times g. So please note that the maximum speed that the object can have without leaving the track only depends on the radius and the gravity, not the mass of the object. Let's look at this scenario now. We're now looking at the same situation, but now we're looking at the bottom of the loop. At the bottom of the loop. And here I'm going to assume the upwards as positive. And I'm going to explain why I do that in a bit. The assess part, I'm looking for the centripetal force. It's in a circular path. And the object is not in equilibrium. The diagram, again, it's a circle. The object is at the bottom of the loop. Force gravity is pulling it down. And force normal, which is perpendicular to the surface, points towards the center of the loop. Please notice here that the force normal's length is actually longer to show that it is stronger than the force gravity. If the force gravity was longer, then the cart would not continue on the circle. Let's do the summation of the force. It would be summation of Fr is equal to Fn minus Fg. Again, because we take upwards as positive. That's why the Fn was positive and the Fg, which is negative. If I solve, I can now make the substitution in here. Okay? And there you go. Please notice, if we have taken the downward position to be positive, then it would look something like this. On a circular path, if you take the direction towards the center of the circle to be positive, you can avoid this. Because if you solve for this problem, notice that this is going to be larger. So it's going to be a larger negative. So in the end, this value is also going to be negative. Because the force normal is the largest value here, and it's going to be negative. This just means that if it's negative, it's going to be pointing towards the downwards position, right? So this is the reason. So it's going to point towards the inner if we take the downward to be positive. Okay? So it depends on how you do it. So if we did it like this, we avoided dealing with the negative. And we just saw that here, the force normal is going to be the largest value. This is going to be the largest value, and it's positive. So this is going to be positive, and if we take positive as towards the center, we saw that it's positive in here. That's why it continues in its circular path towards the center of the circle. Now the question we'll always ask, what is the source of the centripetal acceleration in this problem? What keeps this object in its circular motion? We would say that there are two forces. One is the force normal, which increases it. Then we have force gravity that decreases it. Now a pitcher's arm throwing motion is given here. You're going to derive an equation for the tension on the pitcher's arm in terms of velocity v, mass m, radius r, and the normal force and any other physical constants. There are two situations here. One is when it's on top of the loop of her pitching motion and the bottom of the loop of her pitching motion. Again, her pitching arm is like a string. That's why we can consider it to be tension. In this case, we're going to take the downward position as positive. The assessed part, we're looking for force tension, Ft. It's in a circular path and the object is not in equilibrium. The ball is going through a motion. Let's look at the diagram. The pitcher's throwing motion here can be represented by a circular object, right? Then that is on top of the throwing motion. At the top of the throwing motion, force of gravity is pulling it down. Force tension is also pulling it down towards the center of her arm or her shoulder. At the bottom, force gravity is pulling it down and force tension is pulling it up. Remember, up to her shoulder again. It's always going back to the center, which is her shoulder. Notice which is longer in each one of the scenarios. At the bottom, force tension is stronger. That's why it keeps it in its circular motion. And on top, force gravity is lower. That's the reason why it keeps it in its circular motion. So let's do the summation of the forces and solve. The first part is at the top of the loop. At the top of the loop, it would be summation of Fr is equal to force tension plus force gravity. They're both adding here because they're both pointing downwards. You can make the substitution and solve. You have to subtract mg to both sides so you can get force tension alone. At the bottom of the loop, it's the same equation. Summation of Fr is equal to Ft, but now it's a minus Fg. Why is it a minus Fg? Because force gravity is pointing down. It's away from the circle now. Okay? All right. Give me 1 second. Okay, I corrected it. So, like I said, the downward position is positive. So, the Fg here is positive, so it's plus Fg. Ft is going up, so it's a minus Ft. Good. Now, we make the substitution. Now, what I did here, from here to here, all I did was I divide by -1. Okay, so I can get Ft to be positive. Then I add mg to both sides, so I still get the same value here. So the question asks, at what point in her pitching motion will her arm feel the most tension in her arm? The answer would be here. She would feel the most tension in her arm here. At the bottom of the loop. Because at the bottom of the loop, the force gravity adds to the centripetal acceleration. But at the top, right here, it's a minus. So this, she would feel less on top of the loop. But at the bottom, she feels more of the tension force. Okay? Now it says, looking at only the top of the loop, what is the maximum velocity of the ball can have without flying off the pitcher's hand in that circular motion? So here the velocity is v equals to r question mark. Then we're looking for that velocity. It's pointing to the left because if you see the pitcher's motion, that is the direction of which the ball is traveling. Notice Ft here would be 0 because at the maximum speed the object can have without leaving the loop, that basically means it feels weightlessness. That's why Ft basically becomes 0. So Ft disappears. You have our old problem, m v squared over r is equal to mg. Mass will cancel. Solving for v, you get v equals to the square root of rg. Please note that the maximum speed the object can have without leaving the loop only depends on the radius and the gravity, never the mass. There you go.